Tabular office hours, June 2023, all about optimization. Tabular's automatic table optimization, what it is, why it matters, and how it helps lower your cloud bills as well as improve query performance. So let's get into it. I'm Reid. I'm one of the co-founders of Tabular. I run product here at Tabular. And prior to that, I spent 8 years running data engineering at Netflix, where we did a lot of optimization. But prior to a platform like Tabular, we did almost all of this by paying really competent data engineers to hand tune this stuff. And obviously, we didn't do it for all of our tables. It wasn't cost effective to do that, so we just did on the largest ones. And what we've done with the Tabular platform is really take those concepts and made the platform do them, and that way we can do them for all the tables all the time. And the benefits are fantastic. So without further ado, this is going to be a lot about the economics of optimization. Like at the end of the day, this is about cost and performance stuff. So, when we think about cloud data warehousing, it's actually pretty straightforward. It's nice in the cloud. All this usage-based pricing makes it pretty straightforward for us to think about the cost of any given workload. And so in cloud data warehousing, it's these three components like it is for everything else. You've got your network, storage, and ultimately compute, usually in the form of some sort of queries or data processing. I'm going to use S3 list prices. I think these are like S3 US to East 1 list prices for the purposes of demonstration. Obviously, like your own mileage may vary here. So when it comes to network on data workloads, this is actually the network cost associated with Amazon S3. And a lot of people don't even think about the fact that there is network cost associated with your Amazon S3 usage. Right? They think about, oh yeah, I'm paying for storage, and that's true. That's the bulk of cost. But Amazon does charge you for all the API requests to S3. When you're running queries on large data sets, this stuff absolutely comes into play. We've heard stories of people whose network side of their S3 bill, mostly in the form of GET requests against objects in their buckets, exceeded the cost of their storage. And you'll see in a second like how that can happen pretty easily. So at any rate, these don't look like big numbers, like, for 10,000ths of a cent, is that right? For 10,000ths of a cent for every 1,000 GET requests you make. This doesn't seem like that would add up, but it absolutely can when you get into the millions and millions of objects in a given data set, which can happen pretty easily. So something to keep in mind, and we'll talk about how to optimize this stuff with Tabular's platform. Second part of cost is the most obvious one that we're concerned about, which is storage. And list price for Amazon for storage is basically $23 per terabyte per month. Right? And so the more data you add in your bucket, that price kind of keeps going up over time. A lot of folks kind of keep data forever. They load data in their warehouse in their buckets, and they rarely clean it up. And so this is a number that can start off small, but tends to just grow and grow and grow over time as you collect more and more data. I think about it. We're going to use some analogies of storage you get from like a storage shed you might buy from the local public storage vendor, and you pay X dollars per month for your storage space, and then if you run out of that, you got to keep adding more storage space, and that builds and sort of sits there even though you're not using all that stuff that's sitting in storage. And then the last bit is compute, and this is the number that varies wildly depending on the style of compute that you're using. Right, this can vary a ton if you're using EMR, Spark, or in this case, I've got the pricing here for Amazon Athena, and Athena is actually the most straightforward pricing when we think through this model. But there's lots of different Snowflake credits or Databricks credits. There's lots of different ways that you can pay for compute in your cloud data warehousing environment, and usually it's a combination of the above. Athena actually makes this really straightforward because they actually do it on data volume and not on some sort of compute instance, hours, which is the more typical way. Like, oh, I'm running 3 i6 4XLs at X dollars, per hour, and that can be difficult to think through when you have multiple different queries running on the same nodes. But for the purposes of this demonstration, we'll just use Athena's pricing, which is really straightforward. It basically says for every query you run on Athena, we're gonna sum up the amount of bytes that you scanned as part of running that query, and ultimately just charge you $5 for every terabyte of data you scan. And regardless if you're paying the Athena model or some of the other like compute credit-based models, the underlying concepts are the same. The more data that you have to scan, the more data you have to read in to answer a query, the more expensive it's going to be, whether it's the Athena pricing or in compute hours. And so when we think about optimization at the storage layer, what Tabular is all about is just reducing the number of bytes that any given query has to scan, both through just making that data smaller, as well as organizing it more effectively to match query patterns. And we're going to see all that in action. So those are the big three: network, storage, compute. And just to run through a quick example of how this stuff adds up in a real world scenario. So let's assume for a second that we have some executive dashboard, and we run that dashboard every morning to refresh, the company KPI metrics. And to make the math super simple, let's just assume for a second that the underlying data set, the tables that power that dashboard, total as 1 terabyte of data. This is just for simple math. Let's also assume that terabyte of data is spread across 1 million files on S3, whatever those files are, JSON or Parquet or whatever, at 1 megabyte each. Right. So those are small files, but not uncommon to see that kind of setup where you've got a bunch of small files with a megabyte of data in each file, and you got a terabyte of these things running around. So assuming that we run this query every day, here's how the costs break down. The cost of having this dashboard annually is roughly $2,200 using our S3 pricing models, right? So $146 related to network costs. So that's non-trivial, even though it's 4/10,000ths of a cent, it definitely adds up. It's a little more than half of the storage cost for that terabyte over that year time horizon. And obviously, like in practice, over time, data volumes grow, but we kept everything fixed to make the math easy. And then, the big driver of the total cost, which shouldn't be a surprise to anybody, this is a pretty typical breakdown of what we see in terms of how people spend dollars in their cloud data warehousing environments is the compute. And so, we run this every day, $5 a day, and that's, $1,800 of Athena compute we burn through. So just over $2,200 we would spend annually running this workload. Okay, this is obviously like when we're not doing any of the optimization techniques that the Tabular platform employs. So let's talk about what are the optimization techniques that Tabular employs and how they change this picture. So the nice thing about Tabular, like we mentioned before, it's all automated. You don't have to think about this. You just put data into your Tabular warehouse, and Tabular has a bunch of background processes that are constantly evaluating data being loaded and data being read from your warehouse and making optimization decisions and actually executing compute, which optimizes your storage layout in the background, kind of just all automatically. So this is we're going to use our public storage example here, analogy again. This is nice, right? Let's assume that every one of these storage sheds is some sort of maybe partition in a table. All right, partitions are great. It allows us to organize information. If we only need to get objects from a single shed, we know exactly which one to go and get that from. So that really, we don't have to go searching through all the entire storage just to find the stuff that's my stuff. I know all my stuff is in unit 354. Great. So I can go there and I can open it up and I can get what I'm after. But in a typical scenario, when you're not doing table optimization, you go inside that shed and this is what you find. Inside those partitions, it's a big mess. And so, yeah, I got the shed I wanted, but actually still finding the data inside that I actually need can still be pretty problematic. I might have to sift through all this stuff within that partition in order to get the data that I'm after, right? And it's just not a very efficient use of space or an efficient use of query compute when I go looking for the records that I care about in a given table, all right? And so, Tabular's goal is to make your storage look more like this, right? Just everything's organized in its place, easy to find everything, right? So yes, it's inside partitions, but beyond that, the files that are in those partitions are also well organized, and I can go to the exact file that I need, and then even within that file, get the records that I really care about quickly. So how do we achieve that sort of optimization? And there's really 3 bits. The first one is sorting. So sorting is about taking all the records in your table and organizing them in a way such that data that is similar or is going to want to be queried together is grouped together, right? And so this helps on 2 fronts. Number one, it's going to improve how that data compresses. We're going to talk about compression more in a second. And also it's going to help all the indexing and clustering that you need for query performance. So your queries have various filters, that they're looking for certain data. When that data is grouped together in the same files, Iceberg is really good at returning just the files that are needed to respond to a query, cutting down on how much data we have to read, really saving on our compute costs, and also making those queries a lot more performant. So users are happier because our queries come back faster, and your FinOps folks are happier because your cloud builders are smaller. So sorting is an important part of optimization, and sorting, which columns to sort on is a bit of an art plus science, right? It's a matter of which ones are going to lead to better compression, also which ones are commonly used as filter predicates. So again, this is where Tabular's platform is always looking at all of these avenues and looking at trade-offs on what are the best columns to use for sorting to get savings on size and query performance. We'll see that later in the demo. The second bit is compression. So compression is all about taking the same amount of information and just fitting it into less space, right? So compression techniques, like most common ones, are something like gzip or Snappy, LZ4, Z-standard. These are all different compression algorithms that you can use. And the answer of which one is best is, like most things in data, it depends. And because it depends, you need an automated platform like Tabular to go around and be looking at all your different tables, the different shapes and sizes of data in those tables. And what Tabular's platform does is just constantly does experiments with your underlying data sets, trying lots of different compression settings and looking at the results of each one of those experiments and picking what we think is the best one given the workload for your table. So that's balancing size, write performance, and read performance, because all these different compression algorithms, lead to different output sizes, but also take a different amount of compute on write and compute on read. So we're just always trying to find the best combination of that stuff for your data at a table-by-table level, right? And it's all automated. The next bit, the last bit of optimization is compaction. So, this is the answer to the sort of well-known, I guess, small files problem, right? And this is what we saw in our example data set, is we had a terabyte of data and it was all spread out over 1 million files at 1 megabyte each. And this is not uncommon. We see this a lot in sort of cloud data warehousing scenarios, because the reality is compaction and getting compaction right and doing it in a way that is not disruptive to your operations is a difficult thing to do. Tuning all the settings and making sure it's not interfering with your read and write workloads is hard to get right. Iceberg definitely helps, but Tabular's automated platform really brings a lot of intelligence to how we do compaction, when we run compaction, and how much of the table we compact at a time to make sure that we're not interfering with daily operations in the data warehouse. And so this is really just taking all those small files, packing them together into larger files. Sometimes that means also resorting. Sometimes that means just sort of bin packing those things together. And that just means that when the queries go to read the data, you have a lot less of those network requests. So you're going to see the impact on network requests in terms of number of gets to S3 and all the network overhead that's related to all those gets, and as well as just the I/O efficiency, right? Moving bits from your storage into your compute environment just becomes much more efficient when you've got bigger chunks to move across the wire. All right, so sorting, compression, compaction. Those are the big 3 on how Tabular handles optimization. And what we see very typical for Tabular customers is that the result of those 3 things on any given data set is anywhere from 50 to 80% overall reduction in the size of the data in your bucket, right? So that's significant savings, not a small amount, 50 to 80% overall size reduction. So what impact does that have on actual dollars? On actual dollars. And if we rerun our analysis, considering Tabular's optimization, here's what we find. Right. First of all, like we've cut the 1 terabyte, and we're using conservative numbers of 50% optimization results here as part of Tabular's platform. We go from 1 terabyte to half a terabyte, so that 50% size reduction. And we also took 1 million files at 1 megabyte, and let's just, as an example, reduce that to 2,000 files at roughly 256 megs each. Right. Our network costs, obviously, because we've gone from 1 million files down to 2,000 files, and we're reading those files every single day as part of this query, that drops off significantly, 99, plus% reduction on the network side, right? And that was a small portion, but non-trivial. And so we've gone from what was $146 down to 29 cents, basically making that a non-factor in your cost, which it should be if you're doing these things correctly. On the storage side and the compute side, the math is pretty simple. We just cut everything in half, right? Because you're paying by bytes stored to S3, and if you're using something like Athena, you're paying on bytes read. When we reduce those bytes by half, even though it's the same amount of data, right? Same exact information, we've just really organized and compacted it into a smaller set of bytes. This is the result. You cut those costs in half. Right? Now, there is cost associated with doing all that optimization work. It doesn't come for free, right? This is part of Tabular's platform. We run compute, and part of our usage-based pricing is that we charge you for that compute that we run to do the optimization, right? And the question is well, does that make sense? Do I come out ahead even though I'm paying Tabular to do the optimization? And the answer is, of course, yeah, you come out ahead in a big way, right? In this example, which is pretty realistic, you get 40% overall savings on the cost of that workload, right? And that will be the same across all these workloads, right? Because these are very low-level primitives that we're optimizing. So you've gone from what was a $2,200 a year, dashboard down to a $1,300 a year dashboard, and you do that across all your data workloads, and that can be significant savings, on the cloud data warehousing bills. So that is the math and sort of the technology behind Tabular's table optimization. And we're going to go switch to a demo so we can see what this looks like in practice. All right, real world stuff here. First thing I'm going to show is this is a table that actually is a tabular table, one that we use internally. We use a technology called PostHog to do our product analytics, logging from the browser, what folks are doing on our website. And we like PostHog. It's an open source product analytics tool. It also has a feature where you can have it automatically dump all those events to S3 so that we can easily get it into our data warehouse. Okay. So PostHog dumps all those events into S3, and they roughly have this schema here. And we're using another feature of the Tabular platform, the file loader feature, to automatically take these files in S3 and actually PostHog dumps those as JSON files. So it takes those JSON files and loads them into Tabular's Iceberg tables, and that's just using our file loader feature. You can see that's configured here on the table. So we have file loader enabled. Here's the S3 path where PostHog is dumping these raw JSON files. Right? We've got the JSON format, and we're appending all this data to this Tabular table. All right. We go back and look at the overview for this table. It's got 434,000 rows in it. It's got 175 megabytes worth of data. We can see that the optimization in Tabular is working really well here, as we'd expect, right? File compaction, taking all those small files and making them larger chunks of files. In the last week, we've taken 20,000 plus files and turned it into just under 600. So that's similar to what we saw in our example. And here, because this is JSON text data, and we're turning it into highly optimized Parquet data in this Iceberg table, we're getting incredible storage reduction here. Almost a gigabyte worth of data in the last week has been reduced to 66 megabytes. Right, so those calculations we saw on savings for workloads against this data are going to be much better than the 40%, something closer to 80+%. All right, so that's what we see on the tabular side, and just to show what the raw data looks like, here is that path in S3 where we're loading the JSON files. You can see there's 370,000 files, 444 megabytes. That's the raw JSON stuff, and we saw on the tabular side it's just a few hundred files and just over 100 megabytes. So that optimization is working really well in this scenario. And what does it mean for query performance? So I'm going to hop over here. We're going to run the sample query against this table. This is actually the Starburst Galaxy product, one of the compute engines that you can use with your tabular warehouse. This is a managed version of the Trino query engine. So I've got this connected to my tabular warehouse. I'm going to run a query against this post-hoc events table. And here I'm looking at the referring domain. So where are our users coming from to our tabular websites? And this is just our development scenario, development data. But nonetheless, we can get a sense for where are these users coming from. What are the top 10 domains that are driving traffic to our website? So a pretty common query we might run. And let's kick this off. Oh, I was highlighting the wrong thing. Kick off this query. Wow, that was 1 second. So that's fantastic performance here against what was 400,000 records. And we can see here's our top 10 drivers of traffic. We flip over to the statistics on this. We can see some of the details of how optimization played out here. Of those 400,000+ rows that represent the data set, given some of our filters in the query, we actually only needed up ending to read 18,000 of those rows. So because we've sorted and organized the data well, that's sort of matching up against some of our filters, we were able to cut down the amount of data we had to read quite a bit. And we only had to physically load just under 10 megabytes of data out of the 100+ megabytes of data that's in the table. If we had gone against the raw JSON files, we would see significantly different results. Many more rows loaded because we wouldn't have the sorting, much more physical input, JSON data, string data being loaded up through our query agent. We're not going to get 1 second response times, and that query is going to be more expensive. Our Starburst bill would be higher. So everybody's happy, bills are low, queries are performing well, and that's why we're so excited about the optimization features in Tabular. And I will stop there.